All right, let's talk about something that sounds, well, kind of impossible. How do you actually prove that a self-driving car is safe? I mean, 100% certain. The answer is probably not what you're thinking, so you're going to want to stick around for this. Now, really, think about that for a second. How can you be absolutely sure a self-driving car is safer than a human driver? The obvious answer, right, is just drive it a lot, like millions and millions of kilometers. But here's the thing. Millions doesn't even come close. To get the data you need to statistically prove a self-driving car is safer than us, you'd have to drive it for, wait for it, billions of kilometers. Yeah, billions with a B. That's not a typo. To put that in perspective, that's like driving from Earth to the sun and back more than 10 times over. It's just insane. Okay, so obviously that's a total dead end. You can't run a fleet of cars for literally centuries just to collect the data. This whole brute force idea, it's just not going to happen. It's completely unfeasible economically and just logistically. So engineers had to find a much, much smarter way to solve this.
And that smarter way is a framework called SOTIF. It stands for Safety of the Intended Functionality. Now, this isn't about finding broken parts or software bugs. SOTIF deals with a way trickier problem. What happens when the car is working exactly as it's supposed to, but it still runs into a dangerous situation? You know, like a sensor getting totally blinded by sun glare, or a super confusing intersection. It's all about how you manage the unpredictable.
So how exactly does this SOTIF thing solve that whole billions of kilometers problem? Well, it all kicks off with this really brilliant mathematical breakthrough. The idea is, instead of treating the entire car as one giant mysterious black box, you divide and conquer. The whole strategy here is to stop trying to prove this one massive, impossible thing. This car will never ever crash. Instead, you break that big goal down into a bunch of smaller, totally measurable goals for each part of the car. It's kind of like a series of promises. If the sensors can promise they'll always see an obstacle, and the brakes can promise they'll always work, well then you can mathematically prove the car is going to stop. That's the core of what they call sufficient conditions. Okay, so at the very top level, the math starts with the big picture. This formula here, it's really just a fancy way of stating that ultimate goal we talked about. Make the number of collisions per kilometer really, really, really small. This is that impossible target we started with. But here's where the magic really happens. We can break that huge goal down into two smaller pieces. Think about it. The chance of a collision is really two things multiplied together. First, how often do you even come across something dangerous in the first place? That's all about the environment. And second, when you do see something, what's the probability your car's system actually fails to avoid it? That's all about the car's performance.
And bam, here it is. This is the breakthrough. By just rearranging that math, we get a completely new and way more achievable target. We don't have to drive for centuries waiting for a 1 in a billion collision anymore. Instead, we can focus on something we can actually measure, like proving the perception system's failure rate stays below a certain number.
This right here is the absolute game changer. It takes an impossible driving problem and turns it into a manageable statistics problem. Now we can test for stuff that happens way more often, right? Like a camera missing a pedestrian in a downpour. We can collect data on that and use it to prove the whole car is safe. Okay, but even with this new target, proving that a single perception system is good enough is still a massive challenge. And that leads us to the second big breakthrough, using smart system design, the architecture, to make the whole safety proof even easier. The solution is all about redundancy, what engineers call a multi-channel system. So picture this. You've got two completely independent detectives working on the same case. Detective A, he might miss a really important clue, but Detective B, she could spot it. As long as just one of them cracks the case, you're good. The mystery gets solved. That's the power of having a backup.
Now, for this whole backup plan to work, there are three really important rules. First, each channel, say your camera system and your radar system, has to be able to do the whole job on its own. Second, just one of them working properly has to be enough to keep you safe. And third, the fusion part, the brain that takes the info from both and makes the final call, it has to be rock solid, like basically perfect.
So when does a system like this actually fail? Well, this little cause tree shows us there are basically two ways. The first way is if channel 1 fails and channel 2 fails at the exact same time, but for totally different reasons. Since they're independent, the odds of that are crazy low. The real boogeyman, the thing engineers are really worried about, is something called a common mode failure. This is when one single event,
like a monster blizzard, takes out both of your detectives at the same time. And that brings us to the final and maybe the most important piece of the puzzle. This whole strategy, this whole idea of redundancy, it all hangs on one massive assumption, that those two channels are truly independent of each other.
I mean, how can you be 100% sure that whatever blinds your camera isn't also going to blind your radar? Because if they have the same hidden weakness, then your whole safety net just falls apart. It's got a giant hole in it. So proving they're independent, that is absolutely everything.
So how do they do it? How do you prove independence? Well, engineers use a kind of three-pronged attack. First is the analytic approach. This is all about the design. You use totally different technologies from the get-go, right? Like a camera that sees light and a radar that uses radio waves. Second, you have the experimental approach. This is where you actually try to break both systems at the same time. You throw the worst-case scenarios at them, like insane sun glare, just to see what happens. And finally, there's the methodological way. You just crunch tons and tons of real-world data to show, statistically, that when one system failed, it had zero effect on the other.
All right, let's pull all these threads together. What we're left with is a brand new roadmap for proving that a self-driving car is safe. And it's one that, thankfully, doesn't involve driving to the sun and back.
So check this out. We started with what looked like an impossible problem, but we used math to turn a drive forever problem into a solvable statistics problem. Then we used smart architecture to break one super hard goal into two much easier ones. And finally, we used hardcore, rigorous proof to make sure that whole safety net is actually strong.
And really, this is the main takeaway. Proving a car is safe isn't about brute force, it's not about endless driving, it's about intelligent, targeted validation. It is absolutely about working smarter, not harder.
So all this logic, it helps engineers trust the car they're building. But it does leave us with one last and maybe even tougher question. Is a mathematical proof of safety, no matter how clever it is that enough to earn our human trust? As the people who will be sitting in them or walking on the sidewalks next to them? That's a question we're all going to have to answer for ourselves. Thanks for joining me on this one.